Right, so, hi, I'm Jack, or Strad, I answer both, and my talk today is the clicker working? Is the clicker working? Yes. So, I'm going to be talking about, we've heard from, we want to hit like all these users, we've got some ideas of how to get there, but we've got a few issues to deal with to begin with, which is like actually getting running what we have currently. So, I'll just dive back a little bit first and see where we've come from. In the beginning, shorter transactions worked. We had them started in 2016, it was wonderful. Barely. Things were a little slow, but little memory hungry. Some of those who were doing transactions in the heady days of October, November 2016 might remember computers crashing and so on. Obviously you needed a full node. That's still mostly true, unfortunately. Certainly for a long time only worked on a few Linux-based systems. And as lovely as it is to have finally reached the year of Linux on the desktop, it's not really good enough. Now, fortunately, the last of these items is something that has been able to be worked on more by the community, and I'd like to give a shout out to Radix42 and Kozumarov, I always mispronounce his name, but who did some amazing work on portability over the last few years that we've been able to pull in. So that's not really the focus of my talk. My talk is looking at the other hungry elephants in the room. One of the first things we could look at was the fact that that big memory-hungry cost was the parameters for the circuit that we're using. And so we started off with it being roughly 3 gigabytes that you needed to have. 2.5 of that was the parameters. So we did some engineering optimizations, what we call streamed proving, because you only need some of the parameters in memory at a time. So just pull them when you need them. Great, that halved the memory cost and made transactions take longer. So, win some, lose some, swings and roundabouts and all that. But yeah, we've got to go faster. We want to do better. So the next thing you can start looking at is, okay, what other components of the system can we attack? And the next one was the proving system itself. So the original Sprout proving system that we used was the BCTV 14A paper, which you may have heard recently had some other issues with it in our particular instantiation. But anyway, what we did when we deployed Sapling, we also modified, we redeployed Sprout in a sense. So we took the exact same circuit, added in some optimizations that we found, and deployed it with a new proving system, the same one we used for Sapling. That gave us essentially a 3 times memory improvement, because now you under a gigabyte of memory for that, and halved the proving time. Excellent. We're not done, because that's still not really good enough. Under a gigabyte, that's maybe barely within the reach of phones. And then if you're doing anything useful, you'll get killed all the time in your phone apps. So, okay, well, why are these parameters so large? They're large because the circuit that they contain is large. The circuit is the statement that you're trying to make some proof about, namely that the notes that you're spending previously exist, that they haven't been spent before, that's typically done outside the circuit. The inputs head up to the outputs, all that jazz is handled inside the circuit. So let's make that smaller. So this is essentially what one of the core things we did in the Sapling upgrade. On the left, we have the original Sprout circuit. So that has, it's designed for what we call 2 input, 2 output. So a single proof takes 2 notes to spend and generates 2 new notes. And then you can do some fun things to be able to spend those notes in the same transaction or whatever. But essentially 2 inputs, 2 outputs, standard use case we figured. On the right is the equivalent in Sapling. Now Sapling, another optimization we did was to split the circuits apart. So we now have 1 proof per input and 1 proof per output. So you can see on the bottom there, that little bit down bottom, we have 2 spend proofs and 2 output proofs. That reduced everything by about 90%, which gives you far more space on your computer to do things. And at the same time, it drastically improves the performance of the proving system, and of the proofs that we make, and therefore of the transactions. Now, one of the reasons for that is you'll see, you might be able to see on there some numbers at the top. So the original Sprout circuit was about 1.9 million constraints, around about 2 million constraints. A constraint is just a very simple, A times B equals C, roughly, in R1CS. So just a little mathematical equation, and we build up a bunch of those to form the things we're using. Sapling, I believe, okay, so what actually matters for this, the reason I'm bringing this up is that when it comes to the performance of your circuits, the performance depends on the way you build your prover. And for the particular prover, the way that we built it, for the scenarios we're doing, you have to compute a bunch of what are called FFTs, fast Fourier transforms. And there's a fun property of the way that the proving system operates where every time the number of constraints in your circuit goes past a power of 2, the size of the FT, and therefore essentially the amount of computation you have to do roughly doubles for the particular proving system that we're using. And you can see this on this graph. This was when we were tuning Sapling. We were like trying to pick a particular number for a particular part of the protocol. And so we're just increasing the depth of this tree. It adds like a fixed amount of constraints every single time, and you can see sort of these cliffs that you hit. So the upshot of that was that in Sprout we were just under, from memory, about 2 to the power of 21 constraints. And for the equivalent in Sapling, 2 input to output, it's just under 2 to the power of 18, which is roughly 8 times smaller, and you get some equivalent performance improvements overall. So that covers sort of all the performance aspects of it. But there's one other piece that matters here. So like at this point, we now have 2 to 4 second proofs. Excellent. 40 megabytes of memory. Perfect. That'll let you run on a phone. We want to do better. We want to be able to run on even smaller, more constrained devices. Because, you might have 40 megabytes of memory. What if you only have 40 kilobytes? And this is when we get into the realm of things like hardware wallets and embedded devices, and we want to be able to do what we can on there. Now, I am not an embedded engineer. I know there is some crazy stuff that they can do to run really weird, complex protocols in incredibly constrained environments, but we can make their lives a bit easier. So on the left here, we have the original Sprout key tree. So you can see you have the spending key from which you can derive the incoming viewing key and then the payment address. So whoever's sending you money has the green bit at the top, and then you need the yellow bit to receive your funds, and you need the purple piece to spend. Now, the problem in Sprout was that the spending key was required by the entity making the proofs, because it was you had to make assertions about it inside the circuit. And what that meant is that the person who made the proofs inherently required what we call spend authority, who was able to spend the funds. Now, if you have a device that is unable to make proofs, that device is unable to control who is allowed to make proofs. Because if you have to, you have your untrusted laptop and you want to have some device controlling the funds, you have to send the spending key to that laptop, and then you're kind of screwed because the laptop now has the funds. If if it can get compromised from there, it's all off. So what we did in Sapling is we sort of added a bunch of complexity to the tree, which was real fun to deal with, but the core bit that matters here is the distinction between the spending key and the proof authorizing key. What that enables us to do is to give what we'll call the prover, the proving entity, this proof authorizing key. And that then allows them to do everything that they need to in the full stack. And then that last layer in between the spending key and the proving key, is where we can stick this boundary. So whoever controls the spending key is the one that does the final spend authority by making a signature over the resulting transaction. And that signature can be done in a much more constrained environment, because now we're just doing Schnorr-style re-randomizable DSA signatures. Whereas the entity that has the proofs, you're trusting them with your privacy, because obviously if you're making the proof, you get to see all the private information that goes into that proof. But you then are in a situation where okay, I trust my laptop with my privacy. You think of your standard hardware wallet style use cases. You trust the device you plug it into with your privacy because you're looking at your transactions on there. No one's going to sit there on your hardware wallet and scroll through your transaction history. That's just not fun. So we have all this that's been put in place. So what can we actually do with it right now? Well, We can make shielded transactions on a full node. Let's not do that in this demonstration. We've already had someone do it, in fact, so apologies, Andrew. But I consider that boring. So we could do shielded transactions on a phone. I'm going to leave this as an exercise to those of you in the audience who have Android phones. One note on that, apparently the URL that's on the little card that we gave you doesn't actually work, so we're in the process of fixing that, but that should be working later today, hopefully. So what I would like to demonstrate is shielded transactions in the browser. This is a demo code is available, and feel free to play with it like during the talk. If you actually don't play with it during the talk because you'll interfere with my demonstration. But after the talk, please go nuts. So what I have running on my laptop here is I have a Zcash D full node running on testnet, nice and pretty. I then have the Light Wallet D, which is our sort of summarizing service that we built as part of the reference wallet project. And so I've got this ingester here, which every time a new block comes in on testnet, it's pulling it in, and then puts into this compact block storage format. And then I have a front end that's serving this via gRPC. gRPC, turns out, you can't actually use with a browser because it requires HTTP2, and there's a whole kerfuffle of things. So in fact, you also now need a proxy in place, so I won't show, but I'm running Envoy in a Docker. And then I have just a little Node.js app that is running in the background. So this is all running locally. So let's pull this up. I'm going to go to localhost.com, pull up the terminal side because then you can see what's going on. So this is a Zcash wallet running in my browser. It's currently it stores everything in memory because who has time to deal with local storage? So it's just going to quickly scan. It's pulling data straight off the local node. And there you go, it's finished syncing. You'll note it started at height 500,000 because what we did was we set a checkpoint. So I know that I have no funds prior to that point in this wallet, so there was no point in scanning it. Cool, so now we have a wallet. It's got 20 TAS in there. I'm going to go to the Zcon Swag app and see if anyone did post a... oh, no. Is it going to... Come on, internet, please. Live demos are us. Boo. Okay, I am going to give up on this and go to, here's what I prepared earlier. Get new address. Cool, so here is another test sampling address. Let's just verify it had no balance. Cool, no balance. There we go. Oh, no, here we go. Cool. There we go. Oh, Linda wants some swag. Cool, let's go get her address. So pop that in there. Let's send Linda 5 TAS. That'll do. And click send. Right, so that is now building the transaction. It's going to take a moment. It is doing a one input to output transaction. Now this WASM build, it is currently doing everything completely synchronous, as in I cannot use the browser UI while this is going. Pull request accepted. But what this is going to do is just make the transaction. Takes about a minute in WASM. An equivalent native transaction with Zcash D on my laptop takes about 5 seconds. So, and it's a dual core with hyperthreading. So if you say roughly a factor of 4 improvement when we add parallelism to this, then it's currently about 3 times slower than the native to run this through WASM. And there's probably a bunch of optimizations that we could do. I need to click on this so you can see. There will be some optimizations that we can do, like gearing things out to be specifically designed for WASM. But like the nice thing about building most of this in Rust is that we can get things like this working with not too much overhead. And I'm going to continue just, here we go, excellent. So the transaction has been created. It has been sent to my local node. Unfortunately, the internet is not really working, so you don't get to see it on here. However, I can pull this across to here and go source, CLI, get raw transaction. Oop. Somewhere in there. Oh, that's the whole thing. I want that one. Cool, there we go. So we can see we have 1 shielded spend, that's the note I spent, and we have 2 shielded outputs being the 5 TAS going to Linda and the change. So, cool, in the browser. Right, eventually my internet will come back. Anyway, let's go back to the talk. So that covers transactions in the browser. That's not the demo I originally wanted to do. What I was hoping to achieve was shielded transactions being created with a hardware wallet. I spent a couple of months trying this and was unable to get things working with Ledger as it currently is, mostly because the Ledger Nano S has about 0.5 MB of stack space, and I am not an embedded engineer, so I can't deal with that, particularly in using the full Ledger BTC app, which is what you would want to build this into. What I was able to do was essentially get a proof of concept working of the, of the core sort of signing part. Because all that a ledger needs to be able to do is actually just receive some digest that it needs to sign, ideally receive the transaction in a form that then it can give you a little information on the screen about what it's signing, and then it can authorize it, make the signature, send that back out, and you know it's valid. So I'm just installing it's based on the sample app at the moment that they provide, just showing how to do a signature. So this is going to take a message. It's going to make I think it's do a double SHA-256 because I didn't bother taking that out of the example app, to get a digest of that, and then it's going to make a red jub signature over it with this is not my real passcode, by the way. It's going to make a red jub signature over it using a key that was generated on the device. Cool, so the app's installed, so let's pop up. So on the right-hand side, I have a USB tool that's showing debug logs from the device, and on the left-hand side is the demo running on the laptop. Cool, so I've turned on the app and it's made a private key on the device, just generated a random one. I do not know what it is. Ignore the constants behind the curtain. That was debugging stuff I forgot to leave out. So I'm going to just type in some random message, I don't know, something interesting. And okay, that's sending across. The first thing the app does is generates a public key from that private key, and then it will send it back. You'll notice this does take a little while. It works, but slowly. Cool, so there's the message on the device. So I'm going to click sign. Now it's going to compute the signature. I had to also split this apart to avoid stack problems into individual components. This is not a nice API. Please don't use this in real protocol design. But there we go. Received the signature, sent it back to the device, and verified. Cool, so most 1.8 of my demos worked. So with that in mind, where can we go from here? The primary motivation for this is ecosystem adoption. As we know, we have a bit of a problem with shielded transactions not being used, and the main reason that I see for that is just who do you use them with? And part of this is because there is a plethora of systems that people use to do all the transparent side of things, inherited from 10 years of working with Bitcoin. And they all have their own custom stacks. We built our stuff originally on C++. We have now nice portable implementation of Rust, but people are using Scala, Clojure, PHP, I assume, to do all this. And so it's not enough to just go, oh, we have this nice little library that you can use. You have to provide it to them in a way that works for them. So, for example, wallet providers, they need to be able to add shielded addresses and transactions to their wallets. That's going to require putting things into either a library that they can get in there, or possibly even some custom code that works in there. Same with exchanges. They'll have their own custom stacks that they want to deal with. And yeah, so all of this requires buy-in from partners that otherwise don't necessarily have a good incentive to do so. If they have to expend a bunch of technical energy learning how our stuff works. So we want to make it easy and attractive to do so. One of the things that we started with along these lines is the Android SDK that has come out of the Reference Wallet project, which there are some good, I don't know if there's a talk about it, but there are definitely some workshops that you should attend to learn about this. We want to continue doing that for iOS and JavaScript and some nice embedded ones and so on. And yeah, the upshot here, we have the know-how on the Zcash side, how to all do this. What we don't have, like I said, I'm not an embedded engineer. I'm also not an iOS engineer. What we need here are people, particularly I would love to talk with some community members who are interested in doing this kind of library development, because I would love to get some mindshare going to get some tailored platforms that work for the consumers of these libraries in a way that they understand that they don't need to care about the particular details of the sapling key structures. Extra credit for this, if anyone's particularly interested in doing like efficient implementations of our curve stuff in different languages, that would also be lovely to see, both the compatibility and just like redundancy. So yeah, that's kind of the motivation for my talk, is that I want to enable developers to do their own things so that we don't have to, and force multiply the industry. So yeah, I've got 2 minutes for Q&A.
Okay. Hello. Oh, no. All right.
I can hear you.
Okay. Thanks for the talk. It was very cool. So I wanted to ask about the ledger thing, just because I recently started looking into that. So I guess, right, your curve is not implemented in their firmware, but do they give you sufficient APIs that you can like do the arithmetic in the field that you need to do, or is there some kind of key that?
So we did the entire, what I did for this, my colleagues Sean Bowe and Eric Ogilvie have been working on a new implementation of our Jub crate, which is designed, it's constant time, which is lovely, but also it's designed to work in embedded systems in Rust no standard. So that's what I leveraged for that demo. It still takes a bunch of space on the stack to do these field multiplications and things. So, but I didn't need to rely on anything from Ledger specifically for that. I did use their Blake 2B implementation, so I didn't have to bundle it to reduce the app size. But yeah, my expectation is that this will become significantly easier for the Nano X, which I got one of, and I was going to try and use for the demo, but they haven't released the SDK yet. So once that's out, I'll give it a go on that.
Okay, thanks.
If you have anything else, come talk to me.